Hello, everyone. My name is Hugo. Currently, I'm a PhD student in Rutgers University in the United States. Today, I'll give a talk to introduce our research, N-cubed H-core neural-designed neural network accelerator via FPGA-based heterogeneous computing cores. First of all, I'll introduce the background and the motivation. FPGA can quickly adapt to the various algorithms without steady performance, such as latency and throughput, owing to its reconfigurability. However, prior FPGA-based accelerators heavily use the DSP resource to construct the processing elements as known as the DSP core. However, as another rich on-chip resource, FPGA lookup table is merely utilized to build the computing units as for the batch normalization and activation. Also, the DNN quantization with various speed widths emerges as a compression scheme to minimize the overall model size. The truth is that the DSP core cannot efficiently support the MAC operations with varying bit widths due to the overhead caused by the flexibility. Thus, an FPGA system that supports fully flexible bit widths is desired. Furthermore, to maximize the performance of FPGA-based accelerator, prior works has conducted the design space exploration. But these works either cannot reflect the design parameters of the architecture or do not impose constraints on parameters sufficiently. In summary, the preliminary architecture design of the FPGA-based accelerator mainly has the following drawbacks. One, rich on-chip lookup table resources are not well utilized. Two, a high performance architecture supporting mixed precision operation is absent. Three, lacking the systematic design methodology for the single chip heterogeneous system. Inspired by these drawbacks, we developed the end-to-end optimization framework as a systematic design methodology for the heterogeneous system. Next, I'll introduce our hardware architecture. As shown in this figure, our architecture includes 5 components. One, instruction generator. The architecture is an intra-layer asynchronous and inter-layer synchronous instruction-based accelerator. Thus, the instructions are generally separated into 2 categories, operation instruction and synchronization instruction. They work together for accurate pipelines computation. The key components of the architecture are the heterogeneous computing cores, lookup table core and DSP core, composed of the lookup table and DSP resource on FPGA respectively. 4 is address generator, controls the base address and strives to fetch data from and store data to DDR. 5 is a peripheral buffer connected to computation cores and DDR. Now I'll introduce the computation flow. The weight in each layer is split into 2 partitions for lookup table core and DSP core. These 2 partitions are quantized with different bit weights. The lookup table weight is quantized with 2 to 8 bits, and DSP core weight is quantized with 4 bits. The activation is shared by 2 cores, and so the architecture is an intra-layer asynchronous and inter-layer synchronous instruction-based accelerator. The lookup table core is based on bit serial computation, where matrix multiplication is decomposed into weighted sum of the binary matrix multiplication. Due to this property, the lookup table core supports varying bit weights operate. We adopt Bismol as its backbone. The lookup table core has M activation buffers, the buffer allocated to the row, and the activation buffers has the depth of DAL buff and the width of K. The N buffers allocated to the column are weight buffers. The depth and the width of each buffer is DWL buff and K, respectively. Each DPU reads K bits from the activation buffers and the K bits from the weight buffers simultaneously, then stores the binary dot multiplication results as partial sum. The lookup table core can process M times K times N bits in parallel. For DSP core, a type of input activation date and the wait date are read from buffers into register arrays. The buffer size is shown in the figure and the table. As listed in this table, these architecture parameters are important configuration parameters that affect the latency, which we will introduce in the later. We build the cost and the latency model to bridge the gap between hardware and software. The cost model simulates the resource utilization of lookup table, BRAM, and DSP on FPGA. And the latency model describes the end-to-end inference latency. In the cost model, the DSP core utilizes all the DSP resource available on chip. So DSP-D core equals DSP available. Since we adopt the BISMO as its backbone, we inherit its lookup table cost model. We build our BRAM utilization model based on the buffer size and the physical structure of BRAM on FPGA. For example, the BRAM slice on FPGA has the depth of 1024 and the width of 36 bits. As the computation core is an instruction-oriented computing unit whose instruction pipeline is organized in a specific pattern, we build its latency model via its instruction pipeline, as shown in this figure below. We focus on and trace the instruction streams and execute the engine and accumulate the latency of each phase as shown in this figure. The latency of waiting for fetching data denoted by 0, the latency of execution denoted by 1, the latency of sending signal denoted by 2, and the latency of result phase. To verify our latency model, we test 10,000 design points with design knobs listed on table on the last page using the random generated value, where the result is shown in figure with the prediction error less than 2%. Now I'll introduce the quantization scheme. The hybrid quantization scheme combines the uniform and the mixed precision quantization. For the shared activation, it adopts layer-wise quantization. Tensors in different layers are quantized with different bit weights. However, the weight tensor adopts neural-wise or filter-wise quantization. Filters in each layer computed by DSP core and the lookup table core are quantized with different bit weights. In each layer, neurons are divided for both lookup table core and DSP core computations. We'd like to find the ratios that balance the computation runtimes of each core in each layer. So we define the workload split ratio as the number of filters computed by lookup table core over all filters in that layer. In this table, it shows all our design factors, including both hardware and software related. The range of the hardware-related factors are determined by our cost model and the available resource on 2 devices. We chose the reinforcement learning-based framework for the end-to-end optimization for extremely low balance and negligible accuracy loss. After the agent chose actions, the system will calculate the workload split ratio of each layer for quantization and the model latency according to the latency model we built. With ratio and quantization bit weights, we fine-tune our hybrid quantized model for one epoch to get the quantized accuracy. The reward function tells that when the model accuracy is larger, tells that when the is larger than the target latency we set, the reward will be less than -1. While if the model latency is smaller than the target latency, the reward will be quantized accuracy minus balance. Minus the spaceline accuracy, and then multiply the lambda, where lambda is scaling a factor and equals to 0.01. The reward is always larger than -1, and with larger quantized accuracy, the agent gets larger reward. So our framework aims for both low latency and low accuracy loss. Now I'll introduce the experiment result. Our experiment is based on 2 FPGA devices, DA and DB. They denote the device XC7Z020 and XC7Z045. This table shows the chosen architecture design factors under different framework settings. On device A, we can find that K is greater when the DNN is ResNet. K denotes the computational parallelism of input channels of activation on lookup table core. A larger K allows more input channels to be calculated in parallel, improving the computation efficiency. Compared with ResNet, MobileNet contains depth-wise layers, which occupy 1/3 of the number of layers. Since depth-wise layers has a small number of input channels, the agent tends to assign a small k to lookup table core. It indicates that the lookup table core is more efficient in computing ResNet than MobileNet. Thus, for MobileNet, the agent allocates more VRAMs to DSP core, which allows DSP core compute faster to compensate for the inefficiency of lookup table core. Now I'll give the quantization and the workload split ratio result of ResNet under different devices and target latency. It reveals that the agent assigns more bit width in downsampling layers as layer 8, 13, and 18. To avoid the information bottleneck, higher bit widths are assigned to those layers. For example, 7 bits for lookup table filters and 4 bits for shared activations. When the target latency bound is set to 30 ms, the quantization bit width becomes lower and is a strict limitation. Consequently, the lookup table core latency is reduced and more workload is assigned to the lookup table core to keep the latency below the bound. This proves that the agent can automatically analyze the latency and adjust the bit width and ratio. Figures in this page shows experiments on MobileNet. As said before, a lookup table core is more efficient in computing ResNet than MobileNet. The agent allocates more VRAMs to DSP core, which allows DSP core compute faster to compensate for the inefficiency of lookup table core. For the same reason, the split ratios of many depth-wise layers in MobileNet are 0, which means that the workload of the depth-wise layer is solely assigned to the DSP core for minimize the latency. Also, the workload split ratio of depth-wise layers is lower than point-wise layers. When the bound is set to 5 ms on device A, the bit width across layers is further lowered compared to the 7 ms counterpart. On device B, the configuration of quantization and ratio shows the same trend. This slide shows the evaluation accuracy of our baseline and automatic configuration. It is clear to find the trade-off between the latency and accuracy. The optimal results show that the results have higher accuracy than baseline, and the simulated latency is accurate enough to predict the FPGA measured latency. This slide shows the comparison of our work with the state of the art. Our proposed optimization framework makes better utilization of on-chip resource, consuming more VRAMs and lookup tables to boost the performance. Also, we get a speed up on both FPGA devices. We outperform the work 3 in latency, throughput, and resource utilization with a comparable accuracy, and we output the work 35, 2.48 to 2.89 times FPS when it operates at the same frequency with us. This is our work. Thank you very much.